This video is on the basic ideas of string theory. We're going to look at the basics such as strings and worldsheets and spacetime from the language of topology. So suppose we're studying closed strings. So there's also open strings in string theory, but you could look at a closed string as a function from uh, two manifolds, sigma and m. And what are these manifolds? So the domain is the worldsheet, and the range of this function is space-time. So these are two manifolds that have different dimensions. You have sigma, which is a worldsheet, which is a two-dimensional manifold, and the other manifold is space-time, which is 10-dimensional. So in string theory, you don't have, in general relativity, you have space-time, which has four dimensions, x, y, z, and t. Whereas in here, you have much more dimensions. So string theory is a two-dimensional field theory. You're going from two dimensions all the way to a manifold of 10 dimensions, mapping it over. So if we look closely at sigma, we could abstractly view the row sheet as this blob, which has an open set. Imagine it has an open set with the point on it. And I could create a chart. And when I create a chart, it will map to R2. And this will allow me to define a coordinate for this point. So when I introduce charts. So a very common paradigm is to represent P as tau and sigma, and I'll go over what those mean. So the other part of this function is what we're mapping to, which is space-time. So if you take a point in space-time, you take in this manifold an open set U, and you define a chart in there, you have 9 components. And what these 9 components are is that the first one is always time, CT, and the other 3 are the known dimensions, X, Y, Z. And then you have these curl dimensions, which is represented by a Clabia manifold. So you have these extra spatial dimensions that are at every point. So you have, in superstring theory, 10 dimensions that you're mapping to. So there are a couple things to keep in mind is that the world sheet is not a subset of space-time. Rather, the image of it is a subset. So the world sheet is something that's distinct. The world sheet, the way it looks is dependent upon whether it's a closed string or an open string. So in an open string, it looks very much like a cylinder, where this is an infinite cylinder, and where tau represents time, and it's infinite. And then you have sigma, which allows you to get a loop direction. So this is defined commonly, you'll see in string theory textbooks, is that the row sheet is defined as, in one way, a Cartesian product of a circle and the set of real numbers. This is one common way to look at the row sheet. So there are different representations based on whether you have a closed string or an open string. So if we take a step back, we're basically mapping, from one manifold to other. We're looking at a string as a function, though. What you see in popular science is a snapshot of this function, what it looks like, and when tau is at a particular time. So in the next videos, we'll go dive deep into what metrics are used in the Worldsheet's Lorentzian manifold, and we'll look at in detail what that really means, and then we'll get into how these strings go about, how we can quantize them to get different particles, like photon, electron, etc. And thank you, that's about it.